So this section is about asteroids. So let's start off with a few pictures of them. Here's Gaspra and Eros and Ida, and all of them are actually quite small, 20 miles across, 30 miles across. But asteroids can also be larger. We've got Vesta and Ceres, two of the bigger ones. So all of these are leftovers from the terrestrial formation, pretty much rock and metal. So most of these leftovers are probably so small that they never underwent differentiation. The metals probably never all sank to the center. And most of them are so small they have very weak gravity. For example, you'd only weigh about 2 ounces on Eros. And the gravity is not strong enough for it to force the rock to flow into a spherical shape. So most asteroids look lumpy, but Ceres is actually massive enough that it has slowly flowed into a spherical shape. So Ceres is actually considered an asteroid and a dwarf planet. Most of the asteroids orbit in the asteroid belt, so between Mars and Jupiter. And just because of Jupiter's gravity, it never let these pieces, these leftovers, actually bunch up and just form into one large planet. So when we talked about the formation of the solar system, we talked about the frost line, and so how the composition changed as you got further away. Inside it was rock and metal, and outside the frost line it was rock, metal, and ice. Right. There are other lines in the solar system that we didn't focus on. So as you look at the asteroids in the asteroid belt, you actually find different compositions depending on where they formed. So the asteroids that formed a little bit closer to Jupiter, they're a little bit more carbon-based, so we call them primitive carbonaceous meteorite, or let's just call it C-type. Right? The ones that formed a little bit closer to Mars were a little bit more stony, had a little bit less carbon, so you could call those primitive stony meteorites, or let's just call it S-type. And there is another type of asteroid called M-type, pure metal. But we don't think any of the asteroids in the asteroid belt could form as pure metal. They had to form as rock and metal. So we actually think that maybe a C-type asteroid was big enough to differentiate, have the metal sink to the center, and the rocky and stony materials float to the surface. And then once it's differentiated, boom, you hit it with something else really big, and they shatter. So now you can have pure metal chunks. So these two you could say are primitive, relatively unchanged since their formation, and this one is processed. In 1970, we knew of about 4,500 asteroids, so they are all plotted up here as tiny dots. Let's start off with the yellow dot, the Sun. Mercury, Venus, Earth, Mars, and Jupiter are plotted as well. Okay. The asteroids that stay plenty far away from the Earth are going to be plotted up as green. Earth-crossing asteroids are going to get tiny little red dots. And ones that get a little close to Earth but we're not really worried about are tiny little yellow dots. And as we go through time and discover more asteroids, you'll see new dots appear and then fade to their appropriate color, green, yellow, or red. Notice that the new asteroids that are discovered are going to be on the night side of Earth. Couple things to notice. The asteroid belt, the great big ring, is amazingly obvious. But these dots are not to scale. So even though the asteroid belt looks like it's filled with green dots, right, it's actually still mostly empty space. And even though Earth's orbit looks like it's filled with red dots, Earth's orbit is still amazingly clear. We are tracking all of the red dots that we have found, all of the Earth-crossing asteroids, and as far as we can predict, none of them are a danger to us. But we will continue to look for new ones and track the ones that we already know. So we just saw that the asteroids look like a smooth ring, but if you make a graph and count up the number of asteroids based on the time it takes for them to orbit, you're not going to find a nice smooth pattern. Some asteroids end up getting into stable orbital times, and at some of the non-stable orbital times there are no asteroids. So this little white line in here goes down. There's no asteroids that have an orbital period of 4 years. Okay. And that's because the asteroids that would have had an orbital period of 4 years would be in orbital resonance with Jupiter. They would line up very regularly with Jupiter, who takes 12 years to go around. And so over time, the gravity bumps it into a slightly different orbit with a slightly different orbital period. And so these are called Kirkwood gaps. You're not going to see the Kirkwood gaps on an image like this of the asteroid belt. The Kirkwood gaps are a numeric gap. There are some really other interesting ways that the asteroids are affected by Jupiter's gravity. Okay. Let's say Trojan asteroids. So look at this image here. Look at these teal dots. Okay. So you've got the inner planets, Jupiter going around. Some asteroids have ended up in Jupiter's orbit, and they're 60 degrees ahead of Jupiter in its orbit and about 60 degrees behind in Jupiter's orbit, and we call those Trojan asteroids. And basically, because the Sun is a large source of gravity and Jupiter is a large source of gravity, at those two special spots in Jupiter's orbit, there's a little way they can hang out there in a stable orbit, and they're called the Lagrange points, which I don't think is in your textbook. It won't be on a test at all. But there's 5 different Lagrange points between two large massive objects. So you get these Trojan asteroids that orbit with Jupiter every 12 years. Now, the Hilda asteroids are basically asteroids in the asteroid belt, but they have been pushed into very interesting patterns. So let's map out the Hilda asteroids here and the purple ones. And they meet the Trojan asteroids, and then they orbit faster and get ahead of it, and they basically end up in a triangular pattern. So this got my attention for a while, and I had to figure it out. How can you have a triangular orbit? You don't. In a snapshot, they look like they form a triangle. But if you were to watch just one of them over one of its full orbit, it's in an elliptical orbit. So if this red dot here is Jupiter, or this green dot is a Hilda asteroid, it's on an elliptical orbit, but its ellipse has been timed just right and tilted just right by Jupiter's gravity. That as a grouping of them, you take a snapshot, you'll get a triangle. And so they have been really affected by the resonance with Jupiter. Feel free to spend an hour on Wikipedia chasing this down. It's really interesting. So sometimes an asteroid will impact Earth, and when it is coming through our atmosphere, the object rams into the air and the air compresses, and when the air compresses it also heats. And so a shooting star is actually the flash of light from that heated air that's getting compressed. And instead of calling it a shooting star, you could also call it a meteor. It's the streak of light from the compressed air as the rock rams into our atmosphere. Sometimes the asteroid will get so heated that it could explode in the atmosphere or just disintegrate. But if a chunk of the asteroid does survive, and land on the ground, you could call it a meteorite. Right? Okay. And what people call a shooting star is usually just a little tiny pebble creating a quick flash of light in our atmosphere. If it was something bigger, like maybe a basketball that was hitting our atmosphere, and you get a bigger streak like this, you wouldn't call it a shooting star, you would call it a bolide. Right? It's just extra terminology.